Okay, this video we're going to start chapter 4 of the text. So this is your pre-cal A text, chapter 4. And the next 3 chapters they all involve trig. Okay? We'll talk about this bad boy a little later on down the road, but this is called the unit circle. All right. And we're going to use it to solve trig expressions. We're going to use it to solve trig equations. Chapter 5 focuses on trig functions, so sketching sine functions and cosine functions and how to transform them. And chapter 6 focuses on something called trig identities. This chapter, chapter 4, will look at developing the unit circle, developing our special angles. We'll talk about measuring angles in degrees, which you see on the inside here, and we'll talk about measuring angles in radians, which you see on the outside. So it's another way of measuring an angle. Okay, and then we'll use that information to solve trig expressions, solve trig equations, and so on. All right. For now, we're just going to do like a little introductory review and kind of go over some of the things that will be important in order to be successful in this next section. Okay, so we're going to look at simplifying radicals, we're going to look at Pythagorean theorem, and we're going to look at some basic trig properties. Okay, for starters, root 12. If I ask you to simplify that, okay, the square root of 12, that's equal to, we can do its prime factorization. It's a 4 times 3, right? And a 4 is really a 2 times 2. So 2 times 2 times 3 gives me 12. That's another way of writing the square root of 12. Now, since it's the square root, no index here, it's understood to be a 2, I'm looking for pairs, and I have a pair of 2's. So I pull them out, and I end up with 2 times the square root of 3. All right, 2 root 3 is my final answer. So 2 times the square root of 3 is the simplified version of root 12. Next question, 5 root 27. We're going to do the same thing, the prime factors of 27. Okay, that's 3 times 3 times 3. It's the square root. So I'm looking for pairs only. Well, I have 3 3's, but I can only circle 2 of them. And it comes out as a 3. The square root of those 3's would be 3, or the square root of 9, if you want to think of it like that, would be 3. There's a 3 coming out, there's a 5 already out there, so 5 times 3 gives me 15, and there's a root 3, or a 3 still under the square root side. Okay, same idea here, but I'm trying to add these two terms. Well, the only way you can add radicals is if they're like radicals. So like I can add like terms. If this had 5x plus 4x, I could call it 9x. All right, if it says 5x plus 4y, well, it doesn't simplify. I can't combine x's with y's, just like I can't combine root 8's with root 18's. So it looks like there isn't a whole lot I can do with it. However, we just saw above that I can actually simplify the square root of 8 and the square root of 18. 8 is really 2 times 2 times 2, 3 2's multiplied together. 18, that's 9 times 2, or 2 times 3 times 3, right? 9 times 2. I'm going to circle a pair of 2's, kick it out, and I'm going to circle a pair of 3's, kick it out. This is going to equal 2 times 5, 10, root 2, plus this would be 3 times 4, 12, root 2. When I add those together, I add the coefficients, 10 and 12 gives me 22, root 2. That's my final answer. Okay, just to keep in mind how you work with radicals. So 5 root 3 plus 1 root 3, that gives me 6 root 3. They're like radicals. 5 root 3 plus root 2 does not simplify. Okay, can't add radical 3 to radical 2's are not like radicals, and they don't break down. Okay, the prime factors of 3 are 1 and 3. The prime factors of 2 are 1 and 2. Subtracting radicals, they're like radicals, so you can subtract them. 10 minus 8 would give me 2 root 2. Multiplying radicals, okay, we go coefficient 2 by coefficient 5, gives me 10. And then I go radical 3 times radical 2 to give me radical 6. And the radical 6 doesn't simplify. Prime factors of 6 are 2 and 3. I don't have a pair, so I can't bring anything out. If I have root 3 times 5, I just stick those things together. Root 5, root 3. Anything else? No. So those are just some examples of how to work with radicals. And these are skills that you should already have coming into this course. All right, rationalizing the denominator. Rationalizing means we want to get rid of the radical from the denominator. Denominator is the bottom of the fraction, okay? So the bottom. So 5 over root 2. In order to rationalize, I am going to multiply the top and the bottom by the radical, okay? Whatever the radical is in the bottom. So think about why I would do this. If I square that or I multiply it by itself, okay, I end up getting rid of the radical. Root 2 times root 2, you could call it root 4, but the square root of 4 is just 2. Now, whatever I do to the bottom, I got to do to the top. So I end up with 5 times root 2, or 5 root 2. This is considered rationalized, or in the simplified form of 5 over root 2. They equal the same thing. 5 divided by the square root of 2 is the same as 5 times root 2 divided by 2. All right, another example here. In this one, I'm going to multiply by the radical that's in the denominator. I got to do it to the top and the bottom. So 8 times 1 gives me 8. Root 2 times root 8 gives me root 16. 6 times 1 gives me 6. Root 8 times root 8 would be 8. You could write root 64, but then in the next line, you're going to have to change that to a root 8. I suppose I could have done the same with this root 16 up here. It's 8 times 4 over 6 times 8 is 48. So I end up with 32 over 48. I can divide both of those by 16, gives me 2/3. All right, when there is only one term in the denominator, you just multiply by whatever that radical is in the denominator. So if this was a radical 3, I'd multiply both top and bottom by radical 3. If this was a radical 5, I'd multiply both top and bottom by radical 5. Now, when there's two terms, you've got to multiply by the conjugate. Okay, so what is a conjugate? Well, what's the conjugate of 2 minus root 5? It's the same two terms with the opposite sign between them. Okay, and now I'm going to multiply if I do that to the bottom. So the idea behind multiplying by the conjugate is I'll get rid of the radical from the denominator. So check this out. 2 times 2 is 4. That's 2 root 5. That's minus 2 root 5. And this is minus 5. So those go away. I'm left with a 4 minus 5, which is -1 in the bottom. Now there's a shortcut for doing this, okay? Really, you can square the first or go first times first and then last times last. Because when you multiply something by its conjugate, these two middle terms will always cancel one another. All right? So it'll be first times first, 2 times 2 is 4. Root 5 times root 5 is 5, and it's a negative times a positive, so that term will always be a negative. Because if this is a negative, that's a positive. If this is a positive, that's a negative. Okay, up top, 8 times 2 is 16. 8 times root 5 is 8 root 5. Negative root 2 times 2 is negative 2 root 2. And that gives me negative root 10. Okay. None of those simplify, unfortunately. Root 5, root 2, root 10. Prime 5 is prime, 2 is prime. 10 doesn't break down, it breaks down to 2 and 5. I don't have a pair, okay? So what I end up doing here is I'm going to divide all of those terms by a -1, which will change all of their signs. Okay, so I could write this as root 10 plus 2 root 2 minus 8 root 5 minus 16. Okay, 16 divided by -1, -16. 8 root 5 divided by -1, -8 root 5, and so on. Okay, and I just wrote it in this order because I wanted to put the positive terms first. So that is some work with simplifying radicals. Next, we're going to talk Pythagorean theorem. I won't spend much time on this. We know the formula, a squared plus b squared equals c squared, or some people like to say a squared equals, c squared equals a squared plus b squared, or if you were looking for a squared, you can rearrange it. A squared would equal c squared minus b squared, so on. It's all good, doesn't matter how you label it. Just remember that the hypotenuse is always c. So this side would be c. And the hypotenuse is the longest side of the right triangle, or it's directly across from the right angle. It doesn't matter with these two sides, whether you call this one a and this one b, or vice versa. So filling this in, we're going to get root 5 squared. I just replaced the a with a root 5. I get 3 roots 2 to the power of 2, and I get h squared. You can leave that as c if you like. It's the unknown. Doesn't matter the variables, what you call it. So root 5 squared. Remember, that means root 5 multiplied by itself would give you 5. 3 root 2 times 3 root 2. Write that down if you don't know what it is. 3 3s are 9. Root 2 times root 2 is 4. Okay? So if you want to write this as 9 times 4, that's fine. But understand where the 9 times 4 came from. 3 times 3 gave me the 9. Root 2 times root 2 gave me the 2, not 4. That would be the square root of 4. All right. Equals h squared. So I've got 5 plus 9 times 2 is 18. H squared. I've got 23 equals h squared. I am going to take the square root of both sides. So h could equal plus or minus root 23. And since we're talking about the length of a triangle, I'm going to go with the positive length. Okay. And I don't want to write that as a decimal. Okay. I don't want to call that 4 point something. I'm going to leave it as a radical in simplest form. And 23 doesn't break down. 23 is prime. Okay. There is no prime factorization for 23. That's as simple as it gets. All right. Trig ratios. Okay. Theta represents an angle. It's inside the triangle. These trig ratios you see here, which you should be familiar with, they tell us the relationship between specific sides of the triangle. Now, let's get in the habit of labeling the triangle. Okay? For starters, this is the way, the order I would always label the triangle. Directly across from the right angle is the hypotenuse. Let's go with green for the hypotenuse. Then, depending on where theta is, okay, theta is in the bottom right corner. That means this side over here is the opposite side. I always do it in that order because the adjacent one, adjacent means beside theta or next to theta, but sometimes students have a harder time locating this one, or they always, the tendency is to mix these two up. Okay, hypotenuse is straight across from the right angle, should be no problem finding it. Also should be no problems finding the opposite or adjacent side at this point in the game. You're in grade 12 math. Okay? Sine theta, it's equal to the opposite over the hypotenuse. Cosine theta is the adjacent over the hypotenuse, and tangent theta is the opposite side over the adjacent side. That's all stuff you learned previously, okay? Somewhere along the way, you should have focused on these trig ratios. I know we do it in grade 10 math for sure. Okay, I'm sure you did it in grade 11 math as well. But there's a little acronym for remembering these. Oscar had another helping of apples. Okay, if you can remember that, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Some people also think so, ka, toa. Doesn't matter. I don't care what you do to remember it, but this says sine is equal to opposite over hypotenuse. Cosine is adjacent over hypotenuse. Toa is tangent opposite over adjacent. These are called the three primary trig ratios. These are the ones that you should be familiar with. These guys are called the reciprocal ratios. Okay, and reciprocal just means to flip the fraction. So what we have are cosecant, secant, and cotangent. These might be unfamiliar. I don't know if you've seen these before or not, but no big deal. Just make sure you pair them up correctly. Cosecant is the reciprocal of sine. So if sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. Secant is the reciprocal of cosine. So adjacent over hypotenuse becomes hypotenuse over adjacent. And cotangent is the reciprocal of tangent. So adjacent over opposite would be your cotangent. These are the six primary trig ratios. Sorry, the six trigonometric ratios. The three primary versus the three reciprocal. Sometimes the questions will ask you to find the three primary trig ratios. Some say it'll say find the reciprocal ratio, so you'd only need to find these. If it asks for all six, you need to find all six. If it only asks for secant theta, just find secant theta. Okay? Here's a question. How is that? All right. Where were we here? Froze up on me. Okay, so we're finished with the trig ratios. This is a question from your homework. We'll get it started for you. So it's asking for the six trig ratios. So those were these six things we were talking about. Sine, cosine, tangent, cosecant, secant, and cotangent. I want those six things of angle S. So basically, they're telling me to put theta down here. So of angle X, so angle S. All right, what I need to do first is I need to find my missing side. So a squared plus b squared equals c squared. So I'll go 5 squared plus b squared equals 10 squared. So I'm just filling in my hypotenuse. I'll call this side A, this side B. 25 plus b squared equals 100. Subtract 25 from both sides, I get b squared equals 75. Take the square root. Remember, it could be plus or minus, but I'm going to use the positive. And then do my prime factorization. I want to simplify this. 75 is 25 times 3, or 5 times 5 times 3. I have a pair of 5s. I'm pulling them out. B is going to equal 5 root 3. And remember, I don't want to write it as a decimal. I want to write it as a radical and simplest form. Now, in order to determine the sine of theta, or the sine of angle S, the cosine, the tangent, the cosecant, the secant, and the cotangent. I have to label my diagram. I want to know that this is the hypotenuse directly across from the right angle. Because they said angle S, I know to put theta down in the bottom right corner, which makes this side the opposite side. And by default, or by process of elimination, this is the adjacent. Now, if they switched theta from angle S to angle R, the hypotenuse doesn't change, but these two guys would flop. Okay? This would be the opposite, this would be the adjacent. Not the case in our example. So if I want the sine of theta, or the sine of angle S, it's going to equal the opposite over the hypotenuse. Remember Oscar had, it's going to equal 5/10, which would reduce to 1/2. Cosine theta is equal to the adjacent over the hypotenuse, another helping. So it's 5√3 over 5, over 10. And 5√3 over 10. 5/10 would reduce to 1/2. So I'd have 1√3, or just √3 in the numerator, and 2 in the denominator. And that is in simplest form. Okay, I'm going to leave it there. You can check the Teams page and see if you can come up with the other four. The tangent of theta, the cosecant, the secant, and the cotangent.